Functions are perhaps the most important part of a system requirement. Certainly, without a definition of its functions, there can be no system. And it is the functions the system performs that is where the emergent properties come from. This lecture is about establishing the function or functions of a system in clear, unambiguous terms, and how by analysing that definition we can begin to understand what must be going on within a system, and hence to the approach to the problem of design.
When the European Commission on Cooperation in Space Standards tried to outline the system engineering process from the customer's needs to a completed design, they came up with a diagram like this. This starts with identifying the customer's needs as an input, and then progresses through requirements definition, function analysis, and then system design and analysis and verification through a series of interacting feedback loops before outputting the completed system design. If you've been paying attention, this looks like a series of black boxes connected by interfaces, making it look like a system, and which indeed it is. The system engineering methodology applies all over the place, and we'll see another bit a little later. But the interesting bit of this diagram is that the function analysis box comes after the requirements definition.
The answer is that identifying the functions of the system is part of the requirements capture process. But as we analyse the functions to see how they may be achieved, we begin to get an insight into what has to be going on inside the system, and hence we start the process of design. Inevitably, there is feedback into the requirements, but this process of function analysis really came into its own when computers and software became a significant components of systems. Software is really all functions.
Let me introduce you to a little gadget that I first met when I was a teenager, and I was a little surprised to discover it was still around. It's almost the simplest system you can imagine. Appropriately, it comes in a black box. It has an inside, which you can't see, and a human interface on the outside in the form of this switch. And it has a single and singularly useless function. Let's demonstrate. That was probably too quick for you to see. Let's do it in slow motion. When you switch it on, it emits an irritated sound and then it switches itself off. Its function is to switch itself off. Actually, it's a bit more complicated than that. Its function is to switch itself off when the switch is set to on.
At the other extreme from Bob's irritating black box is another black box, a smartphone. This is full of functions. In fact, apart from the fact it has to be small enough to fit in your pocket and big enough to read the text, almost all that is required of it is functions. We buy it for those functions. That's what it does. And if we were designing such a device, the most important part of the requirements documents, apart from perhaps those constraints on the size, would be to list and accurately define the functions that it was able to fulfill. When we talked about requirements, we noted that every system starts with a need, which from the supplier's point of view, fulfilling that need is the purpose of the system. And for the most part, the purpose of a system is defined by the set of functions that it provides. After all, it is in these functions that the system's emergent properties are expressed. And just as we get a definition of the requirements overall by asking quantitative questions about the need, so we get the functions of a system, which are a subset of the requirements, by asking more precise questions about the purpose. So what characterises a requirement to make it a function? We're going to define a function as a process that creates a determinable output state from a given input state. Determinable means that for any input we can determine what the output will be. But it does not work the other way round. Several different input states could give the same output state. So the input state cannot be determined from the output state.
Let's look at that definition of a function in the context of our black box again. The function of the black box is to switch itself off when the switch is set to on. There are two parts to this. One is the statement of what the box does, to switch itself off, the output if you like. And the second part defines when it is to do this, when the switch is set to on. That's the input part. And each function has a single output, although as Mark mentioned it may have several inputs. So a function is a definition of what the system does. It's the format of a verb. The function of the system is to do something. The function of a washing machine is to clean your clothes. If the system is to have more than one function, we might give them names to identify them, or we might group sub-functions under a common head, so that clean your clothes expands to according to the pre-selected wash cycle. Clean clothes then become the output of the system. But this is not the complete description of the function. A function needs to be defined not only by the outputs provided, but by the inputs required to make those outputs happen. The full syntax of a function requirement statement is outlined here. The function of the system is to do something when these inputs are provided. This definition suggests how we might identify all the functions of a system. We first identify all the possible outputs of the system. Then we ask for each output what inputs are required to make those outputs happen. You might make a little matrix with all the outputs down the side and all the inputs across the top. It isn't important how you do it, but by going systematically through the possible outputs and identifying the necessary inputs, you should have a complete set. It does of course depend on you correctly identifying all the required outputs. Here's a nice simple example I'm going to use again in a minute or two. Suppose that we have a simple scientific satellite whose function is to make scientific observations in orbit and then relay those observations to the ground. Without worrying about what is going on inside the satellite, we can probably also identify a second function, which is that the satellite must be able to reorientate itself appropriately when required, either to make its observations or to talk to the ground. This is the satellite from a functional viewpoint. It has two outputs, sending the data to the ground and maintaining or changing its orientation appropriately. The possible inputs are first the observational data itself, second any instructions received from the ground, and then finally some form of attitude sensing to tell you in which direction it's pointing. You might want to note that while I've deliberately kept these descriptions as general as possible, it's apparent that I'm already thinking about how things might work. The satellite or a part of it might want to point in different directions to make the observations and to talk to Earth, for example. So from all this we could construct a simple functional matrix like this. I put a query in the box for data to Earth instructions from Earth because it's not clear whether we want a spacecraft that automatically downloads the data when it's in the right position or whether it requires a specific command from the Earth to do so. This is not unusual in this sort of exercise. Once we've identified the basic function, there are other questions which you need to ask to get a precise answer as to what the customer wants. Once we have this sort of matrix, we can now start to construct functional statements for each of the two functions. Remember, we start with the output and then attach it to the necessary inputs. So the first one looks like this. The function of the satellite is to transmit observational data to the ground when it's made the observations, it's pointing in the right direction, and it's in communication with the ground. And then a second function could be stated like this. The second function of the satellite is to maintain the required orientation when it's got the necessary sensor orientation data and it has the necessary instructions from the ground. Note that each function has a single output, even though it may have multiple inputs. And the same input may be needed either alone or in conjunction with others to start multiple functions. However, if at the end of this exercise you've identified any outputs without appropriate inputs, or for that matter any inputs without an output, then you're in trouble and you need to think again. At this point we might observe that not all of the outputs of a system will be desirable products. Some, like noise and wastewater, will be an inevitable product of the operation of the system. We call these byproducts, and they may be a little harder to spot because they will not generally be apparent in the stated need or purpose. But either for legal reasons or social responsibility, we can expect them to appear in the requirements as a limiting constraint. Getting a good definition of the functional requirements of a system may be a little tricky. These statements for our satellite were still rather general. Other requirements may be easy to quantify. If the system has to fit in a particular space, or work with a particular power source, or be less than a certain mass, we can ask the questions how big, how much, and how long. But let us return to our washing machine and see what happens when the function is to get my clothes clean. This is my washing machine. Its function is to get my clothes clean, and we need to add, when you've plugged it into the mains, when you set the controls to a particular position, when you close the door, and when you press the start button. It says it's automatic, but actually you have to load the clothes yourself and add the soap powder and select the program you want and press the start button. The machine that goes round and collects your clothes, washes and dries them and returns them to your wardrobe without being asked is called a maid, or more probably your mum. And one of the objectives of a washing machine was to remove the need for you to employ domestic servants. So the machine is not completely automatic. You have to load it with the dirty washing, and you have to put in your soap powder and set the program and press the start button. And there are other inputs which we don't tend to think about, which are there when you've plugged it into the electric mains, when you've connected it to a proper water supply. And these are all the inputs, and they're all fairly well defined. But the output is clean clothes, and we haven't actually defined what we mean by clean clothes. The people who designed the washing machine probably did have a concept of what they meant by clean clothes, and probably they did an extensive testing program to determine just what cycle requirements were that would deliver clothes to that objective. What the machine was actually designed to provide was something that would agitate the clothes and the soap powder in water of a particular temperature for a particular length of time, and then to drain them and rinse them in clean water, and finally to spin dry them at a particular RPM for a further defined interval. If your clothes are not clean at the end of that, but your machine has performed each operation correctly, then the service engineer will assure you that it's your problem and not the manufacturer's. It gets more complicated than that. This machine has 15 different functions you can select on this dial, giving different combinations of the degree of agitation, the temperature of the water, and the spin speed at the end. But it doesn't have 15 separate programs. Instead, it has sub-functions defining the agitation cycle, the rinse cycle, and the spin cycle, each programmed by the selection on this dial. That makes the overall design of the system simpler. But the point is now that each of those functions can be precisely, even numerically defined in a way that getting your clothes clean is not. If you've been keeping up with all this, you'll notice that in the process of getting a clear definition of this function, clean your clothes, we've halfway started to design the system. But in the last lecture on requirements, we said the requirements should tell us what the system should do, not how to do it. And that is why this lecture is called functional analysis. Functional analysis follows directly on from mission analysis, which we talked about in the third video. Mission analysis sets up scenarios in which the system will be required to operate and tells us what the system should do. Functional analysis then enables the functions that are required to achieve this to be defined, and once again as far as possible without telling us exactly how it will do that. The purpose of functional analysis is therefore to gain an overall understanding of the functional requirements of the system, to identify missing or possibly missing functions, to develop top-level definitions of system functions, to provide the framework for meeting the requirements, matching the requirements with functions, and to assist in the specification of external interface requirements. So, as we've just seen, while the basic functions can be described simply, to find out what those statements really mean, we may need to take the statements apart until we can get the precision we need to start a design. And in the process of analysing the initial functional statement in detail, we may need to start making design decisions. Remember that a function does not imply a specific piece of kit, hardware or software, that's needed to implement it. It's very easy to think that because the various parts of a system each have outputs and inputs and carry out processes that provide the outputs required by the inputs, that if we analyse the global functions of a system down to part functions, that we're somehow reproducing the physical structure of the system. Many systems have multiple functions, and the same is true of their subcomponents. And as with all requirements, the functional definitions represent a constraint, what is wanted, and not how it's to be done. If there are alternatives, better ways of providing those functions, it is your job as engineering designers to find those opportunities to do the overall task more efficiently. To see how the process of analysis works, let's go back to that scientific satellite again. As we said before, its function is to collect data from observations and then transmit that data back to the ground. Immediately we know that there's something within our system that collects observational data, the input, and something else that transmits that data down to the receiver station on the ground. We don't know what else there might be in the system, but it's reasonable to assume that we might like to have a third component that can receive instructions from the ground and to tell the satellite when to download the data. That's not necessarily the only way to do it, although it is the obvious one. It's worth reminding yourself in these early stages of establishing a concept that there may be other ways and other options, and that each decision we make closes off a range of possibilities. But in this instance, you and I are a small team and we can make a decision between us. If this was a real project, we'd expect several meetings with specialists at least from the science team, the ground tracking network and the eventual satellite owner to be involved. Now, the fact that we've decided that the data download will only take place when the ground controllers decide implies that within our satellite system there will have to be some sort of memory to store the data until it's requested, and some sort of command system to receive the ground commands and to interpret what the system should do. That first decision has led us to knowing that within the system there is going to be something that has the function of a memory and something else that acts as a command system. Note the emphasis on function. Some early spacecraft recorded observations on photographic film and sent back data by facsimile. But at this stage, it should not take too much imagination to think there might be other things on the satellite that you might like to command from the ground. And there might be other data that needs to come down from the satellite to the ground controllers related to monitoring the health of the satellite. These functions are generally referred to as telemetry and telecommand, and are actually separate functions. We might very well expect that these extra functions will be handled in much the same way as downloading the observational data, and involve the same equipment. So we have a case here where the hardware involved is going to be common, but the functional diagram is not. Furthermore, we cannot expect to continue to analyse the functional requirements in ever greater detail and eventually come up with a map of the hardware. The actual hardware implementation will depend not only on the functional requirements, but on our design decisions about what hardware to use and what the function demands are created by that hardware choice. You can assume here that when I say hardware, it also includes any embedded software. The other thing we've seen from this example is the interrelationship between functions and operations. Not all of the functions of a system will be required to be active all the time, but will relate to the operations that the system is expected to carry out. Understanding the mission and the mission operations should reveal the operational functions of the system and hence the appropriate requirements. And the fact that some functions can be separated from others in time can lead to savings in the system requirements. You may think that the simple scientific satellite example I've been talking about is a nice abstract example for the purposes of teaching. So let me introduce you to the real spacecraft. And it's not orbiting about the Earth, but Mars. Mars Express is a European Space Agency spacecraft launched in June 2003 to provide scientific observation of the Martian atmosphere and surface. The name Express in part indicates that this was seen as a quick and low-cost mission, filling in detail not available from other missions, and in particular data lost through the failure of the Russian Mars 96 mission. The spacecraft was placed in an elliptical inclined orbit about Mars in December 2003. And to keep costs down, the design was going to be based on a cut-down version of an existing communication satellite. One issue with the design of Mars Express was that it needed to look in 3 directions. To make its observations, it had to point its instrument downward to the surface of Mars. But in order to send its data back to Earth, the high-gain antenna needed to be pointed in that direction. Furthermore, it needed to draw power for its operation from solar arrays directed at the Sun. Solar arrays designed for a communication satellite that would normally be in an equatorial orbit around the Earth, but in the case of Mars Express would be in an inclined orbit about Mars, which led to a further constraint on the geometry. That meant that the spacecraft had to fulfill 3 apparently contradictory functions: to point at Mars, to point at the Earth, and to point at the Sun. To do all these things at the same time would have involved adding complex pointing mechanisms to the spacecraft, adding to the cost and mass. Instead, it was decided to separate these functions in time. So the spacecraft would point at Mars to make its observation, then pointing at the Earth to download its data, and finally orienting towards the Sun when it needed to recharge its batteries. That meant a compromise over its ability to make continuous observations, but a large reduction in the cost and complexity of the mission as a whole. In the end, the mission was so successful that the same philosophy was applied to a second spacecraft destined for a different planet in the form of Venus Express. So defining and analysing the functionality of the system requires that we think about operations, or the operational modes that are needed. And getting to this stage means that we're no longer defining the requirements on the outside of the system, but beginning to think about what is happening inside that shell. Function analysis now starts to design the system. The process of analysis, that is the splitting of something into its component parts and keeping track of the links, the interfaces between the parts, is a powerful one which recurs frequently in system engineering. We saw that in thinking about our washing machine, where the function getting my clothes clean breaks out into agitating in soap and water, draining and rinsing, and spin drying, and these are linked together sequentially by follows. In principle, we could take each of these sub-functions down to a further level, to component functions, and as long as the existing links were maintained at the lower level, and new links between the sub-functions identified, the same process could be used to analyse the subsystem components of our system, and also the work breakdown structure of the development project to create the system. But analysis in this way is only one way of trying to understand and document the functional processes required within a system. We may need to work our way through the operational sequences of the system in action, or think of the different operational modes the system may work in, and how it transitions between these various states. Like all system engineering tool, simple analysis should only be used when it helps us to move towards a design, and should be abandoned immediately it becomes an exercise in its own right.
To show function analysis working, we have an example here of a clock. Now, this is one of those cases where to fit the example into a lecture, it is very simple, and you would not really use functional analysis on the development of a clock, but it does show the principle. So we have a need to show the time of day, and I have decided that I will meet that need with a time-telling device. For this device to meet its purpose, it will need to have a means to track time and a means to display that time. We can then go further, breaking down the function to create increasing detail. This is a function analysis or function breakdown in diagrammatic form. The basic advice here is to create only a few sub-functions at a time. These sub-functions are often called children. You should perhaps create only 5 or 6 at the most, remembering that the last box in any split may need to be labelled everything else. This in itself can be an important exercise to establish functionality, but its real value comes when interfaces are added to the breakdown, that is, the inputs and outputs of the various functional elements. Some people, when first faced with this process, find that they have difficulty keeping each of the sub-level breakdowns at the same level. This is an issue, but it may not be that important as long as we maintain the links, the interfaces between the components. Then it does not matter how we got there. Remember that a function is something that links an output to a particular set of inputs. So all the links at any given level represent the functions which have to be defined at that level. Now, at the end of this diagram, the interfaces look a real incomprehensible mess. And that is the reality of complex systems. But if this diagram were in a computer, then the computer can track the interfaces level by level. For example, at the second breakdown level, we're told that there was an interface between the time source generating the timing signal and the logic function that turns that signal into meaningful hours, minutes, and seconds. But at the next level, there doesn't seem to be one. The computer can highlight that there is an interface missing, which we can then add, showing that the interface is between the oscillator and the logic algorithm. There are a few things to note here. This functional breakdown applies to any clock, from a wristwatch to a town hall public clock, which is fine up to a point, but to move to a system design, we're going to need other requirements like the interfaces, the environment, and such like. And that said, notice also how the system design decisions are creeping in. The timer is going to be some form of oscillator. Alternatives like receiving GPS time signals are being ruled out, and that is not a logical consequence of the functionality alone. We've also made a design decision to show hours, minutes, and seconds. This may seem obvious, but it is a design choice. It is not solely the result of functionality. We've included logic and source adjustments. These are only required because there will be a performance requirement. And that performance requirement, again, is not enshrined logically in the functionality. Bob and I have both experienced teams who have tried to follow the functional breakdown with an almost religious adherence to pure functionality and never seen it work. We've also experienced teams who go too quickly into the hardware and thus miss the value of the functional breakdown and the lessons it can treat. But if you treat it pragmatically and let the functionality merge into design decisions almost naturally, then you have the link between functional requirements and system design that the European Committee on Cooperation of Space Standards was highlighting. Well, Bob, when we were discussing the script for this, and I produced my clock example, which, as I have pointed out, I generated over many years and refined to illustrate the point of function analysis, we did have a lot of discussion about it, and you had a lot of concerns about it as an illustration. I think starting with the fact that the early functions didn't look like functions because they didn't have inputs and outputs.
Yes, it's worth remembering this, that a function does something, so it's got an output, but it also needs an input. There, apart from creation of the universe, there has been no function which didn't have a precedent that started it off. And so when you're looking at a function, it's always worth looking at that. What's the input that starts the thing going? And so it's incomplete without that.
Yeah, but it's extremely difficult when the logic is you start from a single point, ideally the purpose. That is almost a creation of universe point for the system, and it is actually only sort of a third or fourth where you really are starting to get
Except
into
as you saw with the washing machine, there's a button that you press on the stop that starts it going.
Yes, but is the on-off button even inherent in the purpose statement? It's something that comes out of subsequent analysis. But I think what we're saying here is there is this theory that somewhere that if you've got the purpose statement, within that purpose statement, like a sort of piece of DNA, the whole of the system is encoded, and all you need to do is then decode the DNA, and the system will pop out at the other end.
In that case, I'd ask, why do we have different gadgets that do the same thing?
Absolutely. I mean, we saw the
Why-
US Air Force air fighter
That's right.
pilots, two companies.
Why are there
Yes.
different solutions
Yes.
to the same purpose?
Yes.
And the answer is that it's not that we don't have adequate knowledge, it's that we have different things which you think are important, different design solutions to the thing.
Yep.
Some part of it is going to be house styles even,
Yes.
things that we're slightly better at. When we talk about performance as a whole, you'll see there that there are different things a system can do
Yep.
that have different values, and the values may be different from one person to another. And so there's a creative aspect to this thing. There's decisions we make, and some of the things we're making decisions even when we're not really paying attention to making decisions.
Yes. Absolutely. But I think there's another point is the sort of the purists who think that you get to the end of a system solely by analysis are missing the key point that a lot of system engineering is actually about synthesis.
Yes.
An example I've often given in spacecraft, if you break down a spacecraft, you end up with lots of different subsystems doing different functions. Then you discover they all need power. Well, if you take the thing logically, then each system has got its own little power system.
No,
You have to synthesize out the fact that there
You
needs
have
to be
to-
a power system, there needs to be a supporting structure.
you have to spot it.
Yeah,
Each subsystem doesn't have to have a separate power system. There is a function that supplies power to the function that that system performs.
yes,
So again, it's a point I've already made,
Yeah.
that we shouldn't confuse hardware and function.
no,
They're not the same thing. And so if we do, it's going to be a functional analysis if you like. If we take a spacecraft to pieces and find there are 57 different bits that all require power, effectively have a functional input of power,
yeah,
then it's your job to spot that and say, hey, we could supply this with one power bus.
exactly. But that's a synthesizing activity.
Yes,
It's
and,
not an
and,
analytical
and it may very, and the interesting thing there is what I just said. Every subsystem has a little plug attached to it where the power goes in, but it doesn't have one wire from that to the power generation. It has a bus,
Yeah,
and spotting that you can do it all with a bus rather than 57 pairs of wires is something that you've got to do. It's a creative thing for you to spot, and it's a very simple thing, and we don't even notice we do it most of the time. But it is something that involves you actually understanding what you're doing.
yeah. And what I've found when I've seen people using this is that they're constantly jumping ahead to the answer they know they need.
Yes.
They will artificially put in a power system early,
Yes.
not following the functionality because they know they're going to need one.
Yes. And they're probably doing the right thing.
They're probably doing the right thing, but it shows that the tool has got to be used with caution and care. It is not a panacea that solves everybody's problems and is the one tool that's going to break system engineering.
Because the tool's not creative.
Yeah,
The-
that's it.
tool-
It can even stifle creativity.
Yes, by paying attention to the detail, forcing you to pay your attention to what the machine wants you to pay attention to, rather than what you want to do.
And I think that's
It's a bit like I thought of this morning. we've all had the experience of ringing the doctors or somebody or the maintenance people, and there's a little voice says, press 1 if you want to do this, press 2, and you'll notice there isn't one that says press 10 for a human being. You're forced down a line that's what the machine wants you to do. It's not answering your question, it's answering its own questions.
Yes, and that's not helping you as a system
That's
engineer.
right.
So I think this is the time where we should perhaps look to the computer programs and the things that you will really find in industry when you get out into the wide world. We saw how the complexity of interfaces built up on even a simple case like this, and that we would need a computer to track the network that was being created. They can be used to track interfaces down from the point early in the breakdown when they are obvious, right down to the morass of detail when we may have thousands of internal interfaces, all of which need controlling. Now, there are specialist computer programs that offer to help you do this sort of thing. At the moment, the clear market leader is the IBM program DAWS. Now, the first thing we need to point out here is that all these programs are sold as requirements analysis or requirement trackers, not just functional analysis. So the logic of functional analysis has been extended, but as we have already argued, it is a logic that we feel is fundamentally flawed. This was starting to be introduced on the Skylon project. That was after I left, but I contacted the guys at Reaction Engines to see if I could use some of the output that they were creating to illustrate DAWs at work. Well, perhaps not surprisingly, the reply was that they felt that would be too commercially confidential. But one of the team produced an illustration based on his previous involvement with the ExoMars project, showing the DAWs decomposition down to the components of the entry and descent module. Here is the top level mission requirements, and they're decomposed into 3 sub-requirements, 1 on the ground segment and 2 on the spacecraft. Note the point about numbering, reinforcing what we said in the requirements lecture on the importance of giving requirements identifying numbers, but note the computer cannot generate those numbers any more than it can actually generate the breakdown. You have to feed those in by hand. One significant feature here, however, is that while this is beginning as a functional requirements analysis, it very quickly turns into a hardware analysis. You have to look hard on this slide, but it's quite apparent by the time you get to the next level. At this next level, the 2 space segment requirements are decomposed into separate requirements on the orbiter module that carries the system from Earth to Mars and providing the in-orbit support, and the entry and descent module that will deliver the rover to the surface. Note the terminology of parent-child, with the children being the parents for the next level. At the next level, the requirements relating to the entry and descent module are broken out. Note here that the program is not just checking functional requirement links, but also the other sites of requirement we identified in the last lecture, like operational constraints and interfaces. Well, Bob, I've seen these programs starting to be introduced, particularly DAWs, and I've not really been very impressed with what they've done. They seem to, as we've said, stifle creativity. They seem to be treated by the master of DAWs as if they are going to be the solution, and we've already discussed that that thinking is probably fundamentally flawed. So what I particularly saw is when they were trying to introduce it late into a program that had already developed its system requirement specs and everything, and they were trying to sort of reel back and try all over again, and they got into hardware too quickly, which is another thing. So all the mistakes we've mentioned, I see them happen in industry using these programs. Are you feeling the same way about them?
Yes, I think, except that I would say, I think that something like DAWs is useful if you're doing something that's established and you need to keep track of a lot of interactions and nothing new, very new is taking place. And in particular, of course, which is where something like DAWs comes from, if you're developing software.
Yes.
and extensive system critical
Yeah. I was going to say,
software.
yes, I think we should do a bit of history here. This technique first evolved in the software industry.
Yes.
And they discovered it worked absolutely wonderfully and marvellously and was enabling them to do things they couldn't otherwise do, became an indispensable tool. And then they came like Moses out of Sinai to the rest of the system
Yes.
engineering world and say, look at this fantastic tool we've got, it's wonderful, it does everything. And it's a little like saying, well, we've discovered the cure for gangrene, you chop the foot off, and then saying, and it'll also cure your common cold.
Yes, and I said safety critical software in particular,
Yeah.
because there it's very important that you know how
Yes.
everything affects everything else and so forth, and you and you actually don't want creative programmers working on the programmers at depth.
Yes. And there's another point I can cut in with a war story. I was involved in the beginning of a project that a chip manufacturer wanted to do as part of our system engineering doctorate program. And they came and they said, we're making these chips, we want a way to verify them. So I naively said, well, why don't you just put every input into every input chip and then look at every possible output? And they said, well, that would take 54 years.
Yes.
So they're relying on these techniques to verify what
Yes.
they've got in their chip.
Yes.
And they wouldn't be able to do it in any other way.
No, that's right. But what?
But
Yes. But we know in real life design
yeah,
that you get other issues that come up.
yes,
We've been talking about functionality, and these are things that are operating in functionality, which is tells you what should happen and so forth. We're not actually talking about another important thing in system design. We ask questions about requirements, about how big and how much. What we miss, if not careful, is the what if questions. What if we don't do it that way? What if we used hardware instead of software to do the job?
I like the sound of that.
Or vice versa.
Yeah.
I mean,
Yeah,
the vice versa is often used.
Yeah.
But there, what if we didn't run everything at the same voltage but had different voltages? And those what if questions are things that lead to creative thoughts. And
Yeah.
90% of them will lead nowhere.
yeah,
But the ones that are important will lead somewhere important.
yes,
And it's and following a set procedure that won't ask what if questions,
no,
because a what if question is always open ended,
yes,
and that's why you employ engineers.
yes. So that is function analysis. It is an important tool, but not the complete panacea for all of system engineering problems that some people would suggest. It is an important, if not essential, methodology for the developments of very complex systems which are entirely functional, like software and microprocessors. But it can also be used as a means to guide the thinking between the functional requirements and a system design. Now, its wider use as a requirement tracker has got to be used carefully. If it is essentially a record keeper for design decisions made by other means, it has a potential role, but it should not be used as a design driving tool. So overall, expect to meet this tool if you get into an industry using system engineering approaches, but treat it with caution.